welding of microchips or powder particles to the rake face of the tool due to high temperature at the chip tool interface is called built-up edge. BUE formation. So what is the problem with the built-up edge formation? If you look at the diagram, so here this is a workpiece and chip is removing from the workpiece by using this is a tool. So here the built-up edge will form. This whatever the projection formed on the rake face of the tool is called built-up edge. This is tool. This is workpiece. Because of built-up edge, accumulation of material against the rake face, that seizes to the tool tip, separating it from the chip. So positive, the advantage is if it is thin, the built-up edge is thin, then the power it lowers the tool wear and less power required for the removing the material. If it is thick, the tool life is poor and poor surface finish. Thin built-up edge lowers tool wear and increases tool life. Thick, in the same way, if the built-up edge is big one, thick built-up edge produces poor surface finish and as well as poor tool life. That means failure of the tool takes place. So to avoid this, decrease the feed, increase the speed or increase the rake angle. To avoid built-up edge formation, decrease feed, increase speed of the cutting tool, speed and rake angle of tool. use lubricant. So if you follow these steps, then you can decrease the built-up edge, avoid the built-up edge formation. So built-up edge formations are takes place only with continuous chips, because in case of discontinuous chips, what happens is, as when the small chip is produced, immediately it is thrown out away from the metal cutting zone. Along with this, microchips are thrown away. Time available for is less. So also temperatures are less due to interface friction between the chip and the tool. So built-up edge formation is with only continuous chip. Built-up edge formation so a small size of built-up edge formation, it is protecting the, as we mentioned, rake face of the tool from wear and tear. Tool life is increases, but if the thickness of the built-up edge increases continuously, it becomes obstruction to the flow of the chip. So the chip producing larger forces on the built-up edge, and the built-up edge may chip away. During the chipping of the built-up edge, at many cases, material of the tool also it carries away from the tool. So tool wear takes place. As a tool wear takes place, tool life reduces. Types of chips. So one is discontinuous chips. Discontinuous chips. So discontinuous chips are produced with brittle materials. First point. These are produced with brittle materials. The workpiece is brittle, then if you do mesh turning or any operation, then discontinuous chips are produced. If you use large feed and depth of cut causes discontinuous chips. Low speed, if the speed is low and time available for curling of the chip is more, so therefore chip bending takes place and there is a breakage of the chip takes place. Use of lubricant. So if you use lubricant, during machining large heat is generated. The temperature of the chip is high, it is expanding. When the cutting fluid is poured on the chip, immediately the fluid is absorbed heat away from the bringing to room temperature. Chip is getting consolidated. So in short period of time, expansion and contraction takes place. So some cracks are generated, leads to discontinuous chips. Small rake angle is also one of the responsible for discontinuous chips. Next one is continuous chips. When do continuous chips will form? What are the factors responsible for formation of continuous chips? continuous chips without built-up edge, because built-up edge forms only with continuous chips. So first one is continuous chips are formed with soft material, soft and ductile workpiece, then only continuous chips will form. Second one is high speed machining. High speed machining, then definitely continuous chips will form. As the speed is higher, time available for adhering the microchips is less, so built-up edge won't form. Low feed and depth of cut. Low feed and depth of cut. So as the forces decreases, heat generated also decreases. Chances of adhering the microchips is less. Higher rake angle. Use of lubricant. So if you use lubricant, no need, built-up edge won't form in ductile materials. Especially continuous chips will form only with ductile materials. So if you are mentioning continuous chips, then if you are without built-up edge means you are using low speed, high speed or low feed. These may be the reasons to get the continuous chips without built-up edge. Another one is continuous chips with built-up edge. So here for continuous chip, first point is same, soft and ductile material workpiece has to be used. Second point is here we have to go for low speed if you want built-up edge formation. Third one is larger feed and depth of cut. Low rake angle. These all is responsible for formation of built-up edge. No cutting fluid. So discontinuous chips is preferable in machining. So even if you are machining ductile or ductile materials or soft materials which generally gives continuous chips, we can use chip breaker to convert the continuous chip to discontinuous chips. Analysis of metal cutting with orthogonal machining. We know that orthogonal is 90 degrees. So angle, the cutting edge is perpendicular to the direction of chip flow. In orthogonal cutting, we need to have few assumptions and few notations. This is fixed for everywhere, the problem wherever we use. This is chip. This one. So initial thickness is T1. T2 is chip thickness. So this one is shear angle. T1 is also called uncut chip thickness. Chip thickness before cutting, that is called uncut chip thickness. T2 is chip thickness. This is the most important. If you have to remember this chip thickness and uncut chip thickness. Alpha is always back rake angle. Even if they mention rake angle, that is called back rake angle. Width B1 equal to B2 equal to B equal to width of the chip. So width assumption is width of the chip remains constant always. L1 comma L2 is equal to length of chip per revolution before cutting and after cutting. Cutting operation. VC equal to cutting velocity. In sometimes they give different name. Relative velocity between tool and workpiece, it is also called as relative velocity between tool and workpiece. So sometimes it's not required they have to give same name, they will ask different names. Relative velocity. Next one is chip flow velocity. Chip flow velocity, the velocity at which the chip flow, or similarly relative velocity between chip and tool. Relative velocity between chip and tool. Similarly VS is shear velocity. Or relative velocity between chip and workpiece. Relative velocity between chip and workpiece. R equal to chip thickness ratio. R is a ratio of the chip thickness, or cutting ratio it is also called. In sometimes in GATE exam they asked as a cutting ratio, they gave name as a cutting ratio, or chip equivalent. So this R value is equal to T1 by T2. It's always less than 1. K equal to chip reduction coefficient. So chip reduction coefficient is nothing but inverse of the chip thickness ratio, that is equal to T2 by T1. It's always greater than 1. Pi equal to shear angle of the shear plane with velocity vector. And we have assumed already that the width of the cutting tool remains constant, width of the chip remains constant. And material, and another assumption is material is always assumed to be incompressible, and volume before cutting and volume after cutting remains constant. Whatever volume reductions taking place in the length direction are to be increased either the thickness or width direction, but as we assumed that width is constant because there is negligible change in the width, so length and thickness has to be variable. Volume in increasing the thickness direction. So volume per revolution before cutting is equal to volume per revolution after cutting. So volume is nothing but thickness into length into width, width, thickness. So volume per revolution here we have to take. So here length revolution means instead of length we need to take cutting velocity. Vc is cutting velocity, T2, Vf is the shift flow velocity, B2. B1, B2 are constant because B1 equal to B2 equal to B. Width we are assuming constant. T1 by T2 equal to Vf by Vc 1. So volume before cutting is equal to the volume after cutting. Volume equal to length into width into thickness, length into width into thickness. Width is constant, T1 by T2 equal to T1 by T2 equal to L2 by L1, that is equal to chip thickness ratio. Here also chip thickness ratio R. So from 1 and 2, if you look at the 1 and 2, from 1 and 2, R equal to T1 by T2 equal to L2 by L1 equal to Vf by Vc. Simple equation which is used to remember. They give one value and they will ask another values. So if you know the relation between chip thickness ratio and thickness, so next relation is relation between the angles, that's more important. These angles are related from the triangle ABC. I will just draw layout diagram. So this one is T1. This one is shear angle pi. This one is alpha, rake angle. It's nothing but back rake angle. Suppose if you take ABC as a triangle where AB is a shear plane, sin pi equal to, from triangle ABC, sin pi equal to BC by AB. BC is nothing but chip thickness, uncut chip thickness. So AB equal to T1 by sin B. Next, similarly, sin 90 minus pi minus alpha equal to BD by AB. D is nothing but this one. So what is BD? T2 by AB. So from equation 3 and 4, AB equal to T1 by sin B, sin pi, equal to T2 by cos pi minus alpha. So T1 by T2 equal to R equal to sin pi by cos pi minus alpha. Simplifying, cos pi minus alpha means you can written as cos pi cos alpha plus sin pi sin alpha. Divide two equations with cos pi. Divide right hand side, numerator divides with cos pi. So R equal to T1 by T2 equal to sin pi divided by cos pi divided by cos pi by cos pi cos alpha plus sin pi sin alpha divided by cos pi. So R equal to T1 by T2 equal to tan pi divided by cos pi cancel, cos alpha plus tan pi sin alpha. After simplifying this entire equation, tan pi equal to after simplifying this above equation, tan pi equal to R cos alpha by 1 minus R sin alpha. This is another important formula to remember. R cos alpha by 1 minus R sin alpha. If we increase the